All right, so we're going to change up the volume discussion here for a minute, and instead of taking a region and revolving it around an axis using a disk method or a washer method, what we're going to do this time is we're going to take a region, a two-dimensional region, and in this case, I've done that with y equals the square root of x, and you can see what I've done here is really in essence I've said, okay, here's the square root of x curve, capped it off with y equals 0, and we bounded it over here with x equals 4. So really all of this region right here, that is going to serve as the base region. And what we're going to do to create the three-dimensional solid is we're going to build up. So imagine if you're looking at this on a two-dimensional plane, we're going to build up from that. So I think before we talk about the calculus, it's important to understand the visual idea behind it. The first thing we're going to do is we're going to use square cross-sections to create this solid. So I have two other snapshots here of what this would look like from a three-dimensional perspective. Let's look at this one first. If you look carefully, you can see that the x-axis is right here, x equals 4 is actually right there, and the curve y equals radical x kind of disappears into this three-dimensional solid. So the base region is right in here, and what we've done is we've stacked squares, and we stacked them according to the size of the curve. So if you think about what we would need to do to find the volume this time, we really need to know what the area of the square is, because then we're going to sum up an infinite number of squares. Now if you look at this view down here, you can see a little bit better. This would be right here, would be the line x equals 4. Right here is the x-axis, and then you can see a little bit better the square root of x curve. All of this is your base region two-dimensionally, but we're building up. And the squares every time, you even notice back here, the squares are only as big as the curve itself. So that leads us to the discussion of, well, how would I set up the volume equation? Well, in this case, like I said before, the biggest thing to understand here is that this requires knowledge of the area of a square. So let's use a different color here so you can see a little bit better. If I took one square, just right here, then the side of that square would be however long this line segment is, and that line segment is completely dictated by how high the curve goes. If I did it here, it'd be a smaller square. If I did it here, it'd be a bigger square. So in every single case, the side of the square was dictated by the square root of x. So I need an area equation, and in order to do that, I really am just looking at side squared. Well, if one side of the square is equal to square root of x, then the area of my square here would be the square root of x quantity squared, or just x. Now that's one square. I need to sum up an infinite amount of squares so that I can actually get the volume of this solid. So let's go to the next page so we can see how that looks. So using calculus notation, we're going to be finding the integral of the area of the square. And in this case, it was the integral from 0 to 4 of x dx. So it's a real easy integral math-wise to do, just x squared over 2, and we go from 0 to 4. We go ahead and evaluate that. That would be 4 squared over 2 minus 0 squared over 2, and that would give you just 8 as your final volume. So you look at that and you might say, oh, that seems pretty easy, and it really isn't that bad. It really comes down to you understanding how we were forming the solid. So let's keep the same function, stay with the square root of x, but this time let's do semicircular cross sections. Okay, again, so we start with our two-dimensional region, right? Here's the square root of x curve along the x and y axis. Here's x equals 4, right? And here's your region. Now think about this. If we're going to find the volume of this solid, a solid formed by using semicircular cross-sections, take a look at the three-dimensional perspective. Here's your x-axis, here's the line x equals 4, and then there's that y equals square root of x vanishing inside that tunnel, so to speak. Every time we took this region and we built up using semicircles. Every time we did that, the semicircle was only as big as the square root of x curve itself. So our volume formula completely changes now because now we need to know the area of a semicircle. So the area now would be 1/2 pi radius squared because we only need half the circle. Well, let's go back to our two-dimensional picture. Think about what that would represent then when we draw just that line segment right there. In the previous problem, it represented the side of a square. Now it represents the diameter. Let's look over here. Same thing. See how it just spans the semicircle? So the diameter this time is really the square root of x. So the radius, which is really what we need to find the area, would be the square root of x over 2. So how does that translate to my volume equation? Well, the volume would be the sum from 0 to 4 of the area of a semicircle, 1/2 pi, and in this case, radical x over 2 squared. So now I'm going to go to the next page. We're going to translate this equation over there so we could do the actual calculus. So we said volume is 1/2 pi. I'm going to go ahead and stick that outside because that's a constant now, 0 to 4. And now we're talking about the radius, which was radical x over 2 squared. We can do a little bit of house cleaning here. Keep that 1/2 pi out here. Let's actually go ahead and square this. This becomes x over 4. And if I really wanted to, I could even take the 4 out so that now I have 1/8 pi. And I'm just integrating from 0 to 4. And look what I wind up integrating. This function right here, which is really just x, that was actually the same function. Whoops. Just highlight that there, right? That was actually the same function we used for the square. So it's really not a coincidence because we are using some similar elements. So what are we left to do at this point? Well, at this point, all we do is just integrate and do our regular calculus. So we have pi over 8 out here. We integrate, that becomes x squared over 2, just like with the square. We evaluate it from 0 to 4. Now we already know the answer from the square when we evaluated from 0 to 4. That was 8. So if we multiply that times pi over 8, the volume now is pi. So a completely different volume because we're using completely different cross sections. Let's do it one more time. This time we're going to use equilateral cross sections. So I want you to try and pick up on all the similarities, but yet the differences as well. So let me get a picture ready. Okay, so let's take a look at these pictures here. We have x-axis, y-axis, line x equals 4. There's the square root of x again, right? Same two-dimensional solid, or two-dimensional picture that we've had the entire time. Okay, now keeping in mind that what we're looking at here, right now this stands for the base of an equilateral triangle. Take a look at that. Every time, how high was the triangle? Well, it was only as high as the curve would let me go. The base was only as wide as the curve y equals the square root of x would let me go. Here you go. Here's your x-axis again. There's the line x equals 4. So what is the area then of a triangle? Well, the area is 1/2 base times height. Now the challenge here is if that's my equilateral triangle and my base is the square root of x because that's what's dictated here by the two-dimensional region, that means every side is the square root of x. The problem is when we go to find the area, the one thing we don't have would be the height. So how can we do that? Well, there's a couple different ways you could do it. One way is to use Pythagorean theorem. Right? Here's just 1/2 of that triangle. We know that this is radical x over 2. This is radical x. So if I go, and this is really, let's call that question mark, or we'll call that b, or we can call it h for height, really. Let's call that h for height. So radical x over 2 quantity squared plus height squared must equal radical x quantity squared. X over 4 plus h squared must equal x. H squared must equal 3/4 x. Think about that. 1x here minus 1x to the fourth, or 1/4 x there. So h squared equals 3/4 x. So the height is actually the square root of 3/4 x. So now, how do I go about finding the volume? Well, the same way I did the square, the same way I did the semicircle. Before we do that, though, if you don't want to find the height that way, there's one other way. So let me just show you that. Okay, here's my triangle, equilateral triangle. I have radical x all around. Well, if it's an equilateral triangle, technically, that means that this is a 60-degree angle, this is a 60-degree angle, and then when I split it with the height, that's a 30-degree angle. So I've created a 30, 60, 90 triangle. And if you remember relationships, which not everybody does, this is radical x over 2, this is radical x, there's the 30-degree side. The 60-degree side, which is what we don't know, will always have to be the 30-degree side times radical 3. So if you really think about that, that's radical 3x over 2. Now you look at that and you go back a page and you say, well, wait a minute, I thought the height was radical 3/4 x. And it is, because think about it this way. If I had radical 3/4 x, right, that's kind of like this. Imagine if I split that radical up like that, you can see how that 2 comes about, right? The square root of 4 is 2. So when all is said and done, what have we learned? We learned that the height can really be expressed as radical 3x over 2. Let's find the volume. So the volume is going to be the integral from 0 to 4, 1/2, base, which is radical x, height, which we just said is radical 3x over 2. Looking very carefully, I can pull out a constant here. I can pull out radical 3 over 4, and then just integrate what will be radical x times another radical x, and lo and behold, guess what you have again? X. So we've seen this before. That's x squared over 2. We evaluate that from 0 to 4, but then we have to multiply all that times radical 3 over 4. So we know from previous problems that would be a volume of 8, but when you multiply it times radical 3 over 4, you get 2 radical 3. So to finish up here, this is the last thing to think about, and I think this is what sometimes people are looking for. They're looking for patterns. So we have these square cross-sections, which have their own volume, right, A to B of the area. What we learn is when we do a semicircular cross-section, that we're still going from A to B, we're still using in the integrand the exact same integrand we were using for the square, except there happened to be this relationship of pi over 8. That will happen every time. And when you have an equilateral triangle, you have this constant out there of radical 3 over 4. Again, we'd be using the same integrand. So that's just a quick introduction into finding the volume of solids by what we call known cross-sections. We call them known cross-sections because we know what a square looks like, we know what a semicircle looks like, we know what an equilateral triangle looks like. But the volume that's different here is we're building these three-dimensional solids by building up from a base region instead of taking the base region and rotating it around an axis.